Hello guys, this is Justin Bibilan and welcome to this episode of Don't Panic, It's Organic.
Hello guys, this is Justin Bibilan and welcome to this new episode of Don't Panic, It's Organic. So for today's lesson, we will discuss about aromaticity. So last week, we discussed about aromatic compounds, we discussed about benzene and reactions involving benzene. And there's actually a special type of a lesson which is actually called aromaticity. So in this lesson, we will distinguish what other aromatic compounds exhibits aromaticity, and if they are not aromatic, then they can also be distinguished as an anti-aromatic, or even there are also compounds that is actually non-aromatic. So how can we distinguish which one is aromatic, which one is anti-aromatic, and which one is non-aromatic? So this is the lesson where aromaticity is a very special lesson, and it is actually very important because usually aromatic compounds are actually very stable, and they are stable structure, they are stable organic compounds, and some of it is actually have biological functions, especially in our body. Okay, so what is aromaticity? Aromaticity is a property of a conjugated cycloalkenes. So take note, this is a cycloalkenes, therefore it is a cyclic with a carbon to carbon double bonds. Okay, and it is actually conjugated, and then you would expect that there is a alternating carbon to carbon double single double single. Okay, because this is conjugated, in which stabilization of the molecule is enhanced due to the ability of electrons in the pi orbitals to delocalize. Hence, the molecule is planar. So what do you mean by delocalize? Because you have your electrons is delocalized, then it's actually what? So your electrons are moving. Okay, they are actually moving around or inside the cyclic or inside the ring. Okay, to attain stability of the molecules. Okay, this is what we call the resonance hybrid. That's what I discussed when we go back to aromatic compounds, or when we go back to benzene. There is what we call the resonance hybrid. Remember the Huckel structure. Okay, there is a resonance hybrid. That's why when we draw the structure for benzene, we just put a cyclohexane. We just draw cyclohexane. Then we will just put a circle at the center, because the electrons there are actually delocalized. They are moving around or inside the ring. Okay, hence you can form a resonance hybrid. Okay, and that molecule is actually should be planar. That means its bond angle for hydrogen carbon hydrogen should be 120 degrees, and it should be planar. Okay, so there are actually 4 general requirements for a compound to be aromatic. Number 1, this should be your check mark. Okay, if you have your compound and you are doubting that this compound is aromatic or not, then you can say you can put this as your check mark. Okay, number 1, it should be cyclic. Okay, number 2, there is what we call conjugated. Okay, that means there is a delocalization of electrons. So there is an alternating carbon to carbon single double single double. Number 3, the p orbital is perpendicular to the ring. Hence, the molecule should be planar. Okay, it should be planar. Then number 4, this is very important. It should obey or follow the Huckel's rule of pi-electron, which is actually 4n plus 2 of pi-electron. Okay, so I will discuss that Huckel's rule later. Okay, so as you can see, the p orbitals, okay, these p orbital lobes there should be perpendicular. Okay, perpendicular to the ring. That should be perpendicular to the ring. Therefore, this structure here should be planar. Okay? So this is a structure of a benzene because your benzene is an aromatic. Okay? That is aromatic. You have your carbon to carbon. This is conjugated. This is cyclic also. And it follows also the Huckel's rule. So I will discuss more on Huckel's rule later on. Okay, remember your benzene. So that is planar because it has also a band angle of 120 degrees. It is a conjugated because you have alternating carbon to carbon single bond. This is also cyclic. Okay. So your benzene is actually a special type of cycloalkane. So it is not a normal cycloalkane. It's because, remember, if you have cyclohexane, this is actually experimentally determined for the delta H of an alkene. If you have your cyclohexane, the delta H is 28.6. But this is actually a heat of hydrogenation. Okay? This is heat of hydrogenation of a cycloalkene. So the heat of hydrogenation of your cyclohexane, which only contains one double bond, carbon to carbon double bond, is 28.6 kilocal per mole. However, if you can put another one double bond, that becomes two double bond. If you have your cyclohexadiene, it actually increase in its hydrogenation. Okay, that is actually more or less twice. Okay, that becomes 54.9 already. However, if you will increase it, or will increase the double bond, you have your 3 double bonds already, you would expect that it should be greater than 54.9, okay, for the heat of hydrogenation, because there are so many double bonds there that will be broken down in order for that to become be hydrogenated. Okay, so you would expect that it should be thrice or 3 times the cyclohexane, but the actual for the benzene is actually lower than 54.9. It is because your benzene is a very stable organic compound. And why does it attains its chemical stability? Because it is conjugated, and it because of its delocalized electron, and therefore this is aromatic compound. So aromatic compounds, these are actually special cycloalkenes because it attains its chemical stability, not just like any other alkenes or cycloalkenes. It's different because it has its own stability. It attains its own chemical stability, okay, because of resonance hybrid, the localization of electrons. Okay? So, aromatic, anti-aromatic, and non-aromatic. So, first, before we discuss or before we distinguish compounds to be aromatic, anti-aromatic, and non-aromatic, there are actually heterocyclic, or I also discussed heterocyclic aromatic compounds on benzene, diba? Or also and I discussed aromatic compounds. I discussed about some heterocyclic. Okay, so there are actually heterocyclic that is also aromatic. But how can we know that this heterocyclic is an aromatic? It is not anti-aromatic or non-aromatic. So when you say heterocyclic, so there is another atom that is present on the ring aside from carbon. So it can be nitrogen or oxygen that is actually present on the ring aside from carbon atom. Okay, but first we will discuss about classification of lone pairs. Okay, before we distinguish that this heterocyclic aromatic compound is aromatic, or it is an anti-aromatic, or it is non-aromatic. So first we are going to know what is the classification, or what are classification of lone pairs. We have what we call delocalized lone pairs, or DLP. These are actually lone pair of a heterocyclic atom or a heteroatom that undergo delocalization through conjugation. That means this lone pair is actually involves or in the localization of electron inside the ring. So it participates in the delocalization of electrons inside the ring. So it's not just all the time that if you can see conjugated, like carbon to carbon double bonds and single bond alternating, then that is automatically an aromatic. Okay, there are also lone pairs that can exhibit the localization of electrons, and it is actually part of the system or of the stability of the compound, because it also part of the conjugation, because that lone pair can undergo delocalization. Remember, for oxygen and nitrogen, your nitrogen has one lone pair. Okay, your oxygen has actually two lone pairs. Okay, so for example, if you have your pyrrole, okay, so your pyrrole or pyrrole is actually an aromatic. This is actually aromatic. Okay, why? Okay, remember it is cyclic. Oh, that is cyclic. Okay, so I will not just discuss that further. Okay, so you have your carbon to carbon double bonds here. That is correct. So you have your single and your carbon to carbon double bonds. And you will expect that, oh, it's not conjugated because there is actually single here. Okay, so how can we know? You have single, single. Okay, so you would expect that, this is not aromatic. Okay, but actually, your nitrogen, it has what we call the localized lone pair. Okay, remember, your nitrogen has a lone pair of 1, and it should be found inside the ring, not outside the ring. Okay, the lone pair of the nitrogen of a pyrrole should be inside the ring, so that this is what we now call the localized lone pair to stabilize your ring. Okay, this is used to stabilize the ring, because without this lone pair inside the ring, the ring is not stable. Okay, it could be broken down by just means of a simple reaction or simple or just in normal condition. Okay, that's why that electron there would now be inside the ring, so that it is now what we call the localized lone pair, and it is now part of the conjugation. Okay, because it can be delocalized, it could be transferred there, and this should be transferred here, and that will be transferred there. Okay, so since there is now what we call delocalization of electrons, the lone pair can also be delocalized if it is actually part of the ring system or part of the ring system. However, there are also lone pairs that is actually on the outside, but in this case, this lone pair is actually found on the inside to stabilize the ring. Okay, so that this lone pair should be part of delocalization through conjugation, and therefore this is what we call the localized lone pair. Okay, remember, okay, I will now discuss the Huckel's rule. Okay, remember, this should be cyclic. That is correct. So is this cyclic? Correct. Okay, that is cyclic. This is planar. That is also planar. Okay, that is planar. Automatic, that is a planar, because you have your double bonds there. This is an sp2 hybrid. Okay, this is sp2. This is also sp2, and that is sp2, and this is also sp2. Then that system there is actually planar. Okay. Then your end there will also contribute to an sp2. Okay. Then what is now the next? So that is a planar. Okay, cyclic planar. We have a conjugated. So this is conjugated. Of course, that is conjugated. You have your carbon to carbon single double bond alternating, and also your delocalized lone pair, which is actually undergo delocalization through conjugation. So therefore, this is also conjugated. Huckel's rule. Okay, remember the Huckel's rule, that is 4n plus 2 of pi electrons. Okay, if n is equal to 1, what would be the pi electrons? If n is equal to 1, what would be the pi electrons? That would be 6. Okay, so n is equal to 1, that is 4 plus 2, that becomes 6. If n is equal to 2, what would be the pi electrons present? 10. Okay, that is 10. Okay, so you should have a total of 6 pi electrons or 10 pi electrons. Okay, remember your double bonds. Each of the double bonds contains 2 pi electrons. Okay? And also your lone pair contributes to 2 pi electrons. So you have your one double bond here that is a 2 pi electrons. You have your also one double bond there that is 2 pi electrons. And you have your one lone pair that is actually used in the localization through conjugation. You have another 2 pi electrons. Now, how many pi electrons are present there? Okay, to stabilize the ring, there are actually 6 electrons. Then, therefore, this follows the Huckel's rule, and therefore, this compound is an aromatic compound. Okay, that's it. There is also another classification of lone pair, which is what we call the localized lone pairs. So, localized lone pairs are actually a lone pair of an heteroatom that actually does not undergo the localization through conjugation. That means it is not part of the making the ring to be stable. It's not part of the stability of making the ring to be stable. Okay, it's not part of the stability of the ring system. Okay, what is this? For example, your pyridine. Okay, your pyridine, this is actually aromatic. Okay, automatic, that is aromatic. Your nitrogen has a lone pair, but where is the lone pair located? Is it inside the ring or outside the ring? Okay, you would expect that we will test first the aromaticity of a pyridine. This is cyclic, correct? That is cyclic. Okay, that is cyclic. Planar, correct? That is a planar. You have sp2. You have sp2 here, sp2. That is also sp2. You have sp2, sp2, and sp2. Okay? You have your carbon to carbon, which has a double bond. That is actually sp2. Remember, your carbon is a double bond. Automatic sp2 hybridized. Therefore, this is planar, 120 degrees. Okay? Then, what are conjugated? Correct. That is conjugated. Conjugated. Okay. That is still conjugated. Remember conjugated? You have your carbon to carbon double bond, single. You have your double bond, single, double bond, single, alternating. That is conjugated. Huckel's rule. Huckel's rule should have 6 pi electrons, 10 pi electrons. Okay. For n is equal to 2, that is 10 pi electrons. For n is equal to 3, that is 14 pi electrons. Okay. So, how many pi electrons are already present here? You have 2. You have also 2 here. And you have 2, that becomes 6 pi electrons. So, therefore, the ring is already stable. Okay. So, therefore, the lone pair of nitrogen shouldn't be found on inside the ring because the ring is already stable. It already follows the Huckel's rule. Okay, so therefore, you should expect that the lone pair of nitrogen should be found outside the ring, not inside the ring, because the ring is already stable because it already follows the Huckel's rule of number of pi electrons. And that lone pair there, which is actually found outside the ring, is what we call the localized lone pair because it will not undergo the localization because it is found outside. Then therefore, there is no conjugation that is happening on that lone pair. Okay, am I clear? Okay, very good. So that is an example of a localized lone pair.